Yes, live. My live.
Show you actually.
It's not showing me.
Seeing you.
It's not coming in.
Countdown is still on 151.
But I've already started broadcast. That doesn't mean anything. Oh, okay. Hello. Welcome to this session. I think as per the clock, we are supposed to start in another 1 minute. So I'll wait for that 1 minute. You are visible fully. Still. It's considerable delay, that's common. Okay, so we can begin this live session. The session was primarily for answering any questions that you might have. So if you see the chat box on the right, please type in your questions and I can think about answering some of them. I can see some 15 people or so are watching. So in case you have any questions, please ask them. So we are in the third week of the course. I believe the second assignment deadline is today. Even if you have a question on the second assignment, if you are solving any problem, you got stuck. Okay, so there's one question from Abhishek Upadhyay. The question says, how do you decide to go for conditional or Bayes theorem? Okay, so that is the question. Maybe I'll try to answer that a little bit. I'm going to share my screen, which will have, which does not have channel location. So I'm going to share my screen in just a little while. So you'll see me write something. Okay, so hopefully you can see me write something on this application. So the question is about conditional probability. Let's say you have two events, A and B. And the main result in all of this is about the probability of A intersection B. Okay, probability of A intersection B, as it turns out, can be written as probability of A times probability of B given A. And also, it can be written as probability of B times probability of A given B. Okay, so this is the essential and most important idea to keep in mind. And what one has to do is this equation is essentially Bayes theorem if you think about it. Okay, so typically what will happen in most problems is you will be able to compute P of A, P of B, P of B given A will be easy to compute. Okay, and then using this rule for probability of A given B, you can find probability of A given B. using this relationship. Using this relationship, you can find that. That's the basic idea in conditional probability and Bayes theorem, etc., etc. So hopefully that part is clear. So you can think of any exam, many examples which work like this. So you might have say two urns, and then let's say you have in one urn you have 4 red plus 5 blue, and another urn you have 6 red plus 7 blue, right? You pick an urn at random, right? And A is an event which says this is urn 1 and urn 2. Urn 1 was chosen. Okay. And then if you look at another event, event B could be that the ball is red. Okay, you pick an urn at random and pick a ball from urn at random. Okay. So in this example, hopefully you can see probability of A is half. That's easy. Okay. And probability of B is, I mean, we're not able to easily think of that, but what's also easy is probability of B given A. Okay. Given that urn 1 was chosen, probability of having red is easy to write down, 4 by 9. Also, what is easy is probability of B given A complement. Okay, what is A complement? Urn 1 was not chosen, which means urn 2 was chosen. Given that urn 2 was chosen, probability of getting a red ball is 6 by 30. Okay. So when you know B given A, probability of B given A complement, and you also know probability of A complement, right? Probability of A complement is also half. So it turns out you can use all of these guys and write down probability of B. Okay, so how do you write probability of B? Probability of B, it turns out, is probability of B given A times probability of A plus probability of B given A complement times probability of A complement. Okay, so you can use this and find out probability of B. Okay, so you can use all of these guys and find out probability of B. Okay, so I can write it down if you like, 4 by 9 into half plus 6 by 13 into half. Okay, so you'll get some number, and then you can go back and use this result, this one result here, and find probability of A given B. Okay, so now you can find. So one can find probability of A given B using Bayes' rule. So that's the idea. So I mean, this is the flavor of the sort of problem you solve with Bayes' rule and conditional probability. In one direction, the conditional probability is easy. In the other direction, you use Bayes' rule to find the probability. Okay, so hopefully this was clear, and I mean you can think about this. Okay, so hopefully that answered Abhishek's question. Okay, so that was one question on conditional probability and Bayes' rule, which maybe I answered in too much detail, but anyway, so I think there is some confusion a lot of people have tried to do that. Oh, okay. So Abhishek is on a questioning spree. So he has a very interesting question on multiple random variables. So let me also Okay. Let me share my screen again and answer this question. So you asked a question about 3 or more random variables with the same distribution and independent. What can you say about which one is greater and with what probability? Okay, so these kind of questions are interesting. In fact, you can say a lot about the order of multiple independent random variables. So these kind of questions are called questions on order. So supposing you have x1, x2, x3, 3 independent random variables. Okay. And you want to find, let's say, so this question is about which one is greater. I guess he meant which one is the greatest. So you want to look at max of x1, x2, x3, right? So this is the kind of question you want to describe. Okay, so what is this? So I should warn you, at this point in the course, we have not yet looked at complicated problems like this. We have not come to random variables and all that in great detail. So this is a question which is looking ahead, but I don't mind quickly answering this question. So many of these questions, so you essentially have to answer this question. A probability that max of x1, x2, x3 is less than, let's say, some x. Okay. So if you think about it, the maximum has to be less than x, and this is actually completely equivalent to the probability that x1 is less than x, or maybe less than or equal to, I put here, doesn't really matter. x2 is less than or equal to x, and x3 is less than or equal to x. Okay. So that's the first step in understanding about order. So maximum of x1, x2, x3, if you want to say probability that it is less than or equal to x, that is the same as x1 being less than or equal to x, x2 being. So if you think about it, it's true either way, both ways. It's true, so this is correct. So now since x1 and x2 and x3 are independent, this probability will simply become probability of x1 less than or equal to x times probability that x2 is less than or equal to x times probability that x3 is less than or equal to x. Okay. So I have managed to break down the probability of max of 3 random variables being less than or equal to x as the product of each of these cases. So now this was true because of the independence assumption. Okay, so this was true because of independence. If x1, x2, x3 are not independent, this would not be true. Okay, so after this, it's not very hard to go ahead and do something. For instance, if you know, say, the CDF of x or the PDF of x, each of these things can be found. And what will follow from here essentially is that the CDF of max of 1x2, x3 is the product of the CDF of x1. So that's just the x1 of x times x2 of x x3 of x. So if all of them have the same distribution, it will simply become fx of x whole to the power 3. Okay. And then how do you find the PDF? You differentiate it with respect to x. So you'll get 3 times fx of x squared times the PDF x of x. So this is the PDF. This guy is the CDF. Okay, assuming they are identical. Okay, so this is where the identical part comes in. Okay, so hopefully this gave you an idea for max. For min also one can do the same thing. In fact, for any other sequencing also one can do some similar sort of arguments. So for instance, if you want to find the 5th biggest and 10 independent random variables, things like that, it's well understood. Sequencing is well understood. Okay, so even for others on the portal other than Abhishek, if you have a question, you can type it on the chat window on the right You should have a chat window. If you're on your mobile, unfortunately, your chat window will not be on. But if you're on a desktop or a laptop, the chat window can be on, and you can type your questions there. I'll be happy to address them as we go along. Okay. So thank you, Abhishek, for questions. Anyone else with some questions? Hopefully, you know how to ask questions. You can't come on video or anything. You have to go on the chat window and type your questions there. Hopefully, that's clear. Okay, so in case there are not too many questions, I'm going to go and look at the questions in, say, assignment 2 and assignment 3, and maybe do some of the problems, at least give you some hints on some of the problems. Maybe that's what I should do. But in case you have any particular question, say in assignment 2 or assignment 3, assignment 2, I believe, is due today. So in case there's any one question that you would like me to give some hints on, be happy to do that. This will be useful for you, or even assignment 3, which is also open. If you have any particular question on assignment 3, I'll be happy to look at that and give you some answers as well. Okay, so there's a couple of questions, one from Rajneesh Sinha and the other from Vishwadit Ghosh. One question is, could you explain the theory of sufficient statistics? Wow, Rajneesh, that's really an advanced question. I'll be happy to explain, but it would require a lot more of background. I'm not sure if I want to get into it right away. But there's another question on why this course is important for electrical engineering. That's an interesting question. So in fact, if you look at my introduction video, I'll spend some time describing why electrical engineering is an important thing why probability is important for electrical engineering. I would urge you to look at the introduction video. I give specific examples. I talk about noise. I talk about estimation. I talk about speech recognition. I talk about so many other things where probability plays a foundational role. In fact, there is a big area called information theory and communications, for that matter, where probability is an integral part. Without advanced probability methods, we will not have current systems. In fact, if you look at communications, particularly if you look at the 5G standard, IoT, etc., probability is the foundation on all of these things. So it's very important to know probability. Let me also look at Abhilash's question. He has a question on some examples on transition probability. Okay, so it's not very clear what he means. Do you mean transition probability of the binary symmetric channel? I'm not particularly clear on what transition probability is. But maybe I should go look at Rajneesh Sinha's course. A question on, okay, so there's one more question. I'm sorry, I'm jumping all over the place. Abhilash, if you can type in what you mean by transition probability clearly, I might be able to say something more. Please go ahead and type in if you get a chance. Now let's look at Abhishek Kumar's question. So he has 3 random variables, x1, x2, x3, which are uniformly distributed in the same interval. And what is the probability that x1 is largest? Wow, this is so similar to Abhishek Upadhyay's question, which I just answered in some detail. So maybe I should just go back and use that example that he has and then do. So I'm going to share my screen once again. You can see in the screen that I've actually solved this exact same problem. Okay. Okay, so maybe this is not the exact same problem that he has asked. So I think his question maybe is a little bit different. So let's look at this question. So he's got x1, x2, x3. All 3 are independent, and he says uniform in the same interval. So let's say take uniform between 0 to 1. That should not matter too much. And he wants to know what is the probability that x1 is largest. Okay. So he wants probability that x1 is greater than x2 and x1 is greater than x3. Right? So this is the kind of question that he has. So what can happen in these kind of questions is one can use some symmetry to come up with the answer intuitively. So if you think about it, x1 and x2 and x3 are all three in the same distribution 0 to 1. So they're all independent. So the answer must be something like 1 by 3, right? If you think about it. So what is the probability that x1 is going to be largest? There is a symmetry here. x1 could be largest, x2 could be largest, x3 could be largest. And whatever area you pick, whatever region you pick, it should happen that x1 would be largest with 1/3 of the probability, x2 would be largest with 1/3 of the probability, x3 would be largest with 1/3 of the probability. So even before doing any great detailed computation, given the uniform distribution in the same interval, I can immediately conclude the answer has to be 1 by 3, because you have you can imagine why that is true, right? So think about why that is true. So the set of values that these three guys take are in the interval 0 to 1, and any one can be greatest with the equal area. So it has to be, there's a certain symmetry here. So one can use symmetry and quickly answer. If you really want to, you have to do this integration and do some solution, but you will get 1 by 3. Okay, so Abhishek, I will throw it back as a challenge to you. You go ahead and do the integration and confirm that this answer is correct, but the answer is 1 by 3. Okay, so you can do it directly. So let me go back to Abhilash's question. He had a question on binary symmetric channel. So he wants some examples on transition probability of binary symmetric channel. So now this is a very fertile area for questions in an area like information theory or something like that. So let me ask you some questions that are simple. So let's say you have transition. In fact, even in your assignment, there is a question, I think. What's the question in the assignment? Well, that's something else. Maybe I'll ask you a slightly different question. So you have one binary symmetric channel. So this is a binary symmetric channel. Let's say P1. Okay. So in fact, it turns out you might want to cascade two binary symmetric channels. So what is the meaning of cascading two binary symmetric channels? What is the binary symmetric channel once again? If you send a 0, you get a 0 with probability 1 minus p. If you send a 1, you get a 1 with probability 1 minus p. The transition is probability p. Okay, so this is P1, so I'm going to put P1 here. So you might want to consider a situation where you have a cascade of two transition probabilities like this. So BSC of P1 and BSC of P2 are cascaded. Okay, so if you cascade, what would be the overall channel? Okay, so it turns out this is equivalent to another binary symmetric channel, okay, with transition probability p. Okay, so it's the exact same thing as a binary symmetric channel p. And what will be this value p? You can try and compute that. This value p is the probability that you get a 1 here, given that a 0 was transmitted. And you could come in two ways here. You could either come here and here, or you could make an error here and come here. And that probability you will see is 1 minus P1 times P2 plus P1 times 1 minus P2. Okay, so this is like some sort of a convolution sort of thing. So a lot of people denote this quantity as P1 star P2. This is just notation. Okay, so this is a nice little problem. Cascade of two binary symmetric channels is another binary symmetric channel. In fact, this P will be worse than P1, and it will also be worse than P2. Okay, see if you can prove that. Okay, so that's another question that might be interesting to you. So this overall P that you get will be worse than P1 or P2. That's kind of easy to imagine why that should be true. but you can prove it, and it's not very hard to write it down and see that it will be greater than both of them. Okay, so this is one simple question, Abhilash. Hopefully you're happy with this. There's one more question from Shankar, who's asked, can you explain one problem on network related? So I guess, so it's asking a question about in the area of computer networking or communication networking, and how probability plays a key role there. So I think most networking problems rely on queuing theory, queues. Okay. So what is the? I mean, there's lots of definition for queue, and this is not very different from a queue that you see in any other place. So usually you have some sort of a server, okay, and then maybe multiple servers, server 1, server 2, server 3. Okay, so this is, I mean, you can imagine, for instance, let's say you have a flight to catch, you're going to the airport, you want to check in, and this is the scenario, right? So there are multiple servers, and there is a queue. There is a queue that is formed, so there will be multiple queues maybe. Okay, so you could have a scenario like this. So you could have 3 queues. Okay, so 3 queues, 1 for each server. Okay, so you might have a system like this. So quite often you have a queuing system where you do something like this, or you might have an alternative in which you just have 1 queue, and for all 3 servers. For instance, if you go to most airports, this is what you will see. You'll see 1 queue for all 3 servers. In fact, most banks you go to now also, they make you stand in 1 queue, and then you go to the first available guy. So now you might ask questions like, which one is better? Okay, so which one is better? Do you want to have 1 queue per server, or you want to have 1 queue for all servers, or multiple queues? What is better? Okay, so these kind of questions are very important, and I gave you simple examples with a queue in front of an airline counter or a bank or something, but you can also have more complicated examples. So this is the same scenario that happens in a router, for instance, right? So the router has these many serving places, and there's lots of destinations are there for the router. So all these packets keep coming, and they form a queue. Okay, and then whatever packet is at the head of the queue is served immediately and sent off. And the packets will have to wait in the queue for a long time, and the queue also has a finite buffer size. I mean, you cannot keep on growing the queue, right? There's only some physical space available on the router, which is limited. So how do you set up these queues? How many queues do you set up in the system? So all of these rely on probability. So you have to model queues probabilistically using probability. So if you read it, there is Poisson models are very, very popular. Okay, so so many other models that you have. So hopefully this give you some rough idea about how networking uses probability. I've not gone into great detail here, but this is the kind of picture that you have to keep in mind. So I gave you a simple example, but even in networking scenario, the same thing is true. So there's a question from Aditya on, will there be any session where we will have examples of applying probability on a communication system? In this course, no. Unfortunately, we don't have too much time for applications of probability. But there are other courses in NPTEL which deal with communications, even signal processing, so many other applications are there. In those courses, I'm sure they are using applications of probability, but we don't have too many applications in this course as such. So hopefully that answers your question. Then there is a question from Abhishek again about what are binary random processes. So that's another subject that we will not do in this course. We will not be talking about random processes in this course. But basically, random processes are you can think of them roughly as sequences of random variables, right? Variables, again, sequences of random variables. And if you want it to be binary, binary basically implies that this has just takes two values, right? The set of two values. Each xi takes only one of two values. It could be 0 and 1, for instance. Okay. And then you would have a binary random process in some sense. That's my understanding of a binary random process. I can't think of any other random process which would be called binary. Hopefully that answered Abhishek Kumar's second question. We seem to have run out of questions again, so there are quite a few people watching still. So maybe in case you have any questions, please go ahead and type it in the chat window. We do have time. The questions can also be related to the assignment problems. I have no problems with that. In case you see an interesting assignment question which you think is complicated or you want more ideas on that, I'll be happy to deal with that also. Please feel free to ask questions on that topic. Okay. So maybe I should clarify something on my own. So in case there are no more questions, I'll take up one of the questions from assignment 3. Maybe I should take that up. So there's a question in assignment 3. Question 9. Okay, I don't know if you've seen this. Okay, this question about telegraph process. No, that's not part of the process. Telegraphy is not something that we deal with. This is a course on basic probability. So let me read out this question a little bit. In assignment 3, question 9, it says there are two independent events and the experiment is repeated till you have independent events, and experiment is repeated till A or B occurs. So what is the meaning of this? You have a sample space. Yes, you have a sample space, omega, and there are two events A and B, and they are independent. So what does that mean? If you say independent, their intersection is definitely not 0, right? So the intersection is non-trivial, and you have a picture like this. The experiment is repeated till A or B occurs, which means the first time you do it, you might get A or B, or you might get something outside of A and B. Okay, so the outcome might be here. So this is outside of both A and B. Okay, so you might have an event outside of A and B. So in which case you will repeat the experiment. If you got an event inside A or B, then you will stop the experiment. Okay, the question asks you to find probability that A occurs before B. Okay, so that's the question here. Now, there is one ambiguity here, which perhaps is not very clearly pointed out in the question. So what happens if A intersection B occurs first? Okay, think about that. So you do the experiment. The first time that you did the experiment, and if an outcome in A intersect B happened, which means what? Both A and B occurred for the first time simultaneously. Okay, so we have to tell you what is the meaning of that. So in this case, we will assume, or we will suppose that A occurs before B. Okay, so it is a little bit ambiguous in the question. It's not very clearly specified. So we will assume that A occurs before B if, say, an event in A intersect B occurs for the first time. Okay, so this one clarification I wanted to give as part of this session because it wasn't very clear in the question. And how do you solve this question? So you have to see how many times the experiment will repeat. If in the first instance you get something in A or B, and if it is in A, then you've succeeded. A occurs before B. But if you get something outside of A and B, so now what is this area? This area outside of A and B is actually A union B complement, right? Complement of A union B. Okay, so that is important to keep in mind. So you can relate these things. I'm not going to solve the problem for you. It's an assignment question. I think I've given you enough hints. You can think about it. You can have a sequence of events and outcomes in A union B complement, and then finally an outcome in A. In that case, you would have succeeded. But if you had a sequence of events in A union B complement and an event in B, then you would have failed. Okay, but A is what is important. You can list all those things and sum up all the probabilities. You'll get your answer. Okay, so that's the idea behind this problem. And anyway, that's a clarification I wanted to give on my own on this question. So I'm going to stop sharing the screen now and maybe wait for somebody to ask a question. Okay, there's a question from Abhilash. In assignment 2, 7th, we need to start probabilities from 4 trials to infinity, forming the infinite GP. In this case, the answer I got was 1 by 8. Okay, so he's contesting a question, assignment 2, 7th question. This one is actually a question that is currently out, as in deadline is not yet over. Okay. Okay, so let me answer Abhilash's question. So Abhilash, you should think about it. I don't think you need infinity in this question at all. Okay, so think about this question. So there's no need for any infinity here. So maybe I should go to this question, assignment 2, question 7. Okay, so remember this. The question says the dice is rolled once or twice. Okay, so I'm sure I'm reading the same assignment. Assignment 2, yes. Question number 7. There is a die which is rolled. A die is rolled, 4-sided die. It's rolled once or twice. That's it. There is no infinity here. Okay. Okay, you roll it once to see if what answer you got. If the result is 1 or 2, you will roll it once more. Otherwise, you will stop. Okay, so which means what is the meaning of otherwise? You will stop. If you got 1 or 2, you will roll the die once again. If you got 3 or 4, you'll anyway stop. Now, the total number of rolls is at most only 2. You don't roll. You don't keep on rolling. Okay, so I think maybe that part is a little bit confusing to you. Think about it. You roll the 4-sided die. If you got 1, say, you roll it only once more. That's all. Stop. Nothing more. You don't keep on rolling. There's no infinite rolls here. Okay, so only once or twice. Okay, no more rolls after that. Okay, so think about that once again. Abhilash, you go back and read it. You understand what I mean? There is a die. It's rolled once. If you get 1 or 2, you roll it once again. But if you roll it twice after that, you stop. Okay, think about it. Okay, so the question about assignment 3, 6th question. Let me look at that. Okay, so maybe a picture will help here. Assignment 3, 6 question. There are 3 towns in a district. Question 6. Okay, there are 3 towns A, B, C. So these kind of questions, a picture is good to draw. Okay, it's easy to draw a picture. I'm drawing a picture here. Say there are 2 roads between AB and 2 roads between BC. Okay, so there are 2 roads here, 2 roads here. So once again, I won't give you the complete solution. I'll just give you a way to think about it. Each of these roads is blocked by snow with a probability P, independently of others. Snow probability is P. Snow on road, probability is P. I'm sitting in Chennai. We never have snow in Chennai, so there's no problem. But I guess if you are in Leh or Ladakh or Shimla or Manali or some nice place like that, you do have the possibility of snow on the road. So this question is for people like that. So, and whether there's snow on one road is completely independent of whether there's snow on any other road. Now that's completely unrealistic, but that's the model given here. Okay, so independent. So independent means you can multiply probabilities. That's all. It's the main thing to remember. So now there are 2 events that they are interested in. A and C are disconnected. Okay. The other event is A and B are disconnected. Okay. So now in many of these questions, you can use a lot of logic and do it, or you can do it in a dumb way. So there's so many here, you can list it out slowly, and then you have to understand this event, and then you also have to understand the event of. So you have to find the probability of what is asked is probability of A and B disconnected given A and C disconnected. Okay, so this is the question that is asked. So if you want to answer this question, you have to find 2 things. This is clearly probability of A and B disconnected, comma A and C disconnected, divided by probability of A and C disconnected. Okay, both A and B are disconnected and A and C are disconnected, divided by probability that A and C are disconnected. Okay, so this is what you need to find, and so I've given enough hints. You write down the sample space in terms of which roads are closed, which roads are open, and the probability for each of them. You will get an interesting answer. So I don't want to give you too many more hints beyond this. So you basically write down the sample space. It has 4 different values, right? So there are 4 roads here. So you will have 4 different possibilities, and each of that will have a probability. So for instance, I'll tell you, supposing you call this road 1, road 2, road 3, road 4. Okay, so you put down 1, 2, 3, 4, and you say, for instance, disconnected, connected, disconnected, connected. Okay, so what is the probability of this? Okay, there are 2 disconnections, P squared into 1 minus P squared. So likewise, you write all possibilities. There are 16 of them. And then you group it into when A and C are disconnected, A and B are disconnected. When both are disconnected, then divide, you get the answer. Okay, so sort of a table method is very useful in these kind of questions. Okay, so there's a question from Karthik Mahajan. He's asked, will there be an advanced version of the course, something that picks up from where this course ends? So let me stop the sharing of the screen and answer this question. So there are a lot of advanced probability courses in NPTEL itself. I'm not aware of a course that's offered in the MOOCs format, but I would encourage you to go to nptel.ac.in and look at the courses. There's one course by Professor Krishna Jagannathan, He's a faculty in IIT Madras. He has taught a very advanced probability course. It's based on measure theory. It's in case you're interested in measure theory and you want to learn the measure theoretic version of probability, you should look at that course. It's a very, very well structured course. It is not a MOOC. We have not offered a MOOC in that area, but you can look at the lectures. All the lectures are there. It's the exact same course he teaches here for our M.Tech students, incoming M.Tech and MS and PhD students. So it's a very advanced course. It's a very nice course. I'll recommend. Other courses I'll recommend are on statistics, probability on statistics, estimation theory and all that. So a lot of courses on that area also. I would recommend those kind of courses, but I don't think we will offer a MOOC directly going forward, an advanced version. But what might happen is, so this course is an 8-week course. We might have a longer version of this course with additional topics as a 12-week course coming forward, maybe in a future semester, but not too much advanced. I think the measure theoretic version by Professor Krishna Jagannathan, I would really recommend. It's a fantastic course if you're looking for a really advanced course in probability. Okay. So there is okay. So there's a question from Akhilesh. Let me address that. It's an interesting question. So Akhilesh has asked following question. He says, hopefully I understood it correctly. He's asked, while solving a problem of conditional probability and shortening the sample space according to the given condition give required probability. Okay, so that's a nice question. So let me answer that question. So let's take a simple example. We'll take a sample space, which is, let's say 1, 2, 3, 4. Okay. Let's say the probabilities, so this is the outcomes. Then the probabilities, I'll say are, let's say, I'll give different probabilities here. So maybe 0.1, 0.2, 0.3, 0.4. Okay, so these are the probabilities. Okay, probability of 1 is 0.1, probability of 2 is 0.2, probability of 3 is 0.3, probability of 4 is 0.4. You can see that it adds up to 1, so it's a proper probability assignment. It's not wrong. Now, let's say I have an event. I don't know, you could call any event, but let's say the event is 3, 4. Okay. So now I am given A has occurred. Okay. So Akhilesh is asking, now that I know given A has occurred, I don't have to consider the entire sample space 1, 2, 3, 4. I can shorten it or make it smaller. Shorten is a sort of a technical term, maybe to make it smaller. So I can sort of restrict to the sample space, which is just 3 and 4. So the theory of conditional probability does exactly that. It tells you should restrict. But then, what is the probability that you assign to 3 and 4? Okay, so that's the important question. You can't say 0.3, 0.4, right? Why? Because 1 clearly does not add up to 1. Okay, so what is the probability you should put there? That's where the conditioning will tell you what to do. Basically, the probability you put there will be 0.3 by 0.7, 0.3, 0.4 by 0.7. So that's the theory of conditional probability. So this guy is the probability of A. This guy is the probability of 4 intersect A. Okay, 0.4 by 0.7. So yes, you can shorten the sample space or reduce the sample space to the event A, but then the probabilities you assign to the outcomes in your smaller sample space have to be normalized by the probability of A. So you have to divide by A. Okay. Okay, so Abhilash is still confused about the question on die rolling. So I think the question maybe worded in a little bit of a. So the question says sum total of the rolls is 4. So you should remember that. So when they mean the sum total of the numbers that showed up in the roll, they have to add up to 4. That's all it says. Nothing more. Okay, don't be confused. The actual question is the die is rolled either once or twice. That's all. Nothing more than that. You're not rolling the die more than twice in that question, Abhilash. Believe me, that's the correct answer. Okay, so if you do that, you'll get the correct answer. Okay, so that's hopefully settles Abhilash's question. Still, maybe the wording has confused him a little bit. Okay, now Shankar has asked some question on assignment 3, third question. So let me look at that. Okay, so I'm looking at the third question of assignment 3, and that question says, coin with probability P. So let me just write that down. Assignment 3. Question 3. Okay. A coin with probability P of coming heads is tossed repeatedly. The head count and tail count are set to 0 before tossing. That's okay. Probability that 3 heads show up before 3 tails. What? Okay. So this is a bit of an interesting question. So you have a coin tossed repeatedly. Okay. And you want 3 heads to show up before 3 tails, right? Three tails. Okay. So in all these questions, let's try to think of this event. Okay, what is this event? 3 heads before 3 tails. Okay, and try and include all the possibilities that will satisfy this event. So for instance, you can have something like this: H, H, H. Okay, so you toss 3 times, you got 3 heads, right? That means you're done, right? So at that point, it doesn't matter what happens after that. You got 3 heads before 3 tails. Okay, so you can stop there. So that will have a certain probability. Now, what else is possible? You can have H, maybe P, H, H. Okay, so even here you can stop. I got 3 heads, and there was only 1 tails. So I can stop here. This will give you another probability. All these guys you can add, they're all mutually exclusive. So likewise, you have to list out all possibilities. And simply add the probabilities. Okay, so if you do that, you will answer this question. Okay, so I'm not going to give you more detailed solution than this, right? So you list out all the possibilities where 3 heads will come before 3 tails can come, and then simply add the probability. So this one will, each of this will have a probability, right? So it's P cubed. This is P cubed into 1 minus P, etc., etc. So you add up all those things, you'll finally get an answer. Okay. So now the next question is from Karthik. He's asked, can you explain this, please? This is from book by John and Dimitri. I think Karthik, I mean, if you're trying to paste some image or something, I think it's not happening. So I'm not able to really see what you have pasted from the book. You have to type it out in text, I think. Okay, then Sheila has asked a question about question 10 of assignment 2. Let me just look at that. Okay. Question 10 of assignment 2. Okay, so there are 4 identical looking batteries, of which 2 are defective. First, 1 battery is selected uniformly at random. From the remaining 3 batteries, a second battery is selected uniformly at random. Probability that both the selected batteries are not defective, given at least one of them is not defective. Okay, so that's the question. There are 4 batteries, 2 defective. So you choose 2 batteries without replacement, right? That's what happens. Battery 1 is chosen at random, and then you have battery 2. And there are two events that you're interested in. First event is one of them is not defective. One of the batteries is not defective. Second event is both batteries are not defective. Chosen at random without replacement, right? This is what is happening here. Both batteries are not defective. Okay, so any question that's given in English like this, I always find it convenient to write it in terms of sample spaces and events and all that. I think that's very important. So that's something that's very important. So you have to write it in terms of sample spaces and events and all that. It will make it much clearer. So if you're not used to that, that's very important skill to pick up when you solve problems. So probability of B given A is what is asked. Okay. So this is the question. So how do you find this? The probability of B intersect A divided by probability of A. So you have to find probability of A. One of the batteries is not defective, which means what? Battery 1 could be not defective, or battery 2 could be not defective, or both could be not defective. So this B is the last case. Both batteries are not defective. Okay. So you find each of these things. So this will actually, if you think of B intersect A, that will be the same as B. Okay. So more or less what you have to find is probability of B by probability of A. Okay. So compute the probabilities. You're choosing two things at random without replacement. That's easy to do. Once you do that, you'll get the answer. Okay. So hopefully this is clear. So that's important. Now there's a question from Srikanth. Maybe I should stop sharing my window here because the other question is not very technical. So there's a question from Srikanth on saying, is it asking me if it's compulsory to enroll for NPTEL courses? Now, from my side, I won't say it's compulsory, but you might be in a college, you might be in a university, which makes it compulsory for you. Okay, so I would definitely encourage you to do it. I think NPTEL courses are nice to learn from. You should, hopefully your college gives you the freedom to pick the course that you want to study, in which case you can really make a choice. But even otherwise, I think you're being exposed to a good quality teaching, and I think you should really enjoy that. I mean, of course, at the end of the day, I'm not doing anything by compulsion, but you know, at some point, it's also good to do good things. And I think if NPTEL courses are quite nice in some way. If you enjoy them, you should definitely do it. Okay, so that's my my answer to your maybe complicated answer to your simple question. Hopefully that answered your question. Hopefully that's clear. Okay, so I think we are coming close to the end of the live session. There's a question about which book needs to be referenced. There is a book that that we have actually mentioned in the outline itself. So if you go to the main course page, there is a book that we have referenced here. It's not a suggested reading. We give two books suggested readings. So maybe I should I'm going to cut and paste from that into the chat window. Okay, hopefully that will clear. So these are two books that we recommend. The first book is very nice, Introduction to Probability by Bud Sekas and Sid Seklis. I'm not sure if it's available in cheap edition. I think it is. But definitely the second book is also very nice, Probability, Random Variables and Stochastic Processes. Papoulis and Pillai, that's definitely available in cheap edition. You can buy that also. So that's a good book as well. Okay. There's a question about signal processing and communication. Okay, so now Well, that's slightly off topic, but for signal processing, the classic book is Oppenheim and Schaefer, which is pretty good. I think for a basic introduction, I think Oppenheim and Schaefer is really good. You should look at that. For communications, there's a wide variety of books, and the latest book that I would recommend is a book by blanking out on the name. Just give me 1 minute. Okay, so there's a book on communications by Upamanya Madhav. Digital communications by Upamanya Madhav. I would definitely recommend that. Of all the books that I've seen, this is a modern book. It has communications by Madhav, Upamanya Madhav. It's a very good book. I would really recommend it. It's nice and practical, and you'll really pick up a lot of digital communications. Also for GATE exam, I'm not really very sure. I can look it up and tell you later on. But for now, I'm not sure what is good for GATE exam. But if you really want to learn digital communications, the book by Madhav is very good. But GATE maybe uses a slightly more classical book, like maybe Simon Hayes or something like that. But I like Madhav's book for what it teaches. Karthik has been asking a question on expectation. So this is the last question I'm going to answer, because you said he's really asked me carefully to say it. I understand. So I think I will stop with this last question from Karthik Mahajan, which is a question on expectation. So this is the last question I'm going to address, and after this, I will stop. So the question is on expectation. Karthik has asked, we have not really covered expectation yet. And if you wait till the last week, week 8, expectation is covered in detail. Okay. And Professor Aravind particularly deals with the case when expectation is not defined. This is clearly addressed by Professor Aravind in that week 8's lecture. I would definitely urge you to be patient. You will get it in week 8, so don't worry about it. But to give you a brief flavor, the Cauchy distribution is the famous distribution for which expectation is not defined. I believe the distribution is something like 1 by pi into 1 plus x squared. This is the PDF. Expectation is not defined. So don't worry, it's coming in some great detail in your week 8 of the lectures. Okay, so I'll stop with this. I think thanks a lot for participating. So many of you asked very interesting questions. Hopefully, I've been able to explain this. I'm happy to do this again if there is enough interest. But please do post questions on the forum. Forum is also a possibility. In case you're really keen on one more session like this, I'll be happy to do it next week or the week after that. I'm happy to answer your questions. So please let me know on the forum. And thanks a lot once again for your participation. Okay, thanks. I'm going to stop the broadcast now. Thank you very much. Stop.